Chapter 6, Kinetic Energy and Work. Kinetic energy and work covers kinetic energy, work and kinetic energy, work done by a gravitational force, work done by a general variable force, work done by a spring force, power. You can find them in the timeline. Kinetic energy. Newton's laws of motion allowed us to analyze many kinds of motion. However, the analysis is quite complicated. There's another sometimes more powerful technique for analyze motion. This other technique involves energy, which comes in a great many forms or types and could be extended to other situations, such as chemical reactions, geological processes, and biological functions that do not involve motion. In fact, the term energy is so broad that a clear definition for it is difficult to write. Technically, energy is a scalar quantity that is associated with a state of one or more objects. The term state here has its common meaning. It is the condition of an object. However, this definition is too vague to be of help to us now. In this chapter, we focus on only one form of energy, kinetic energy. Kinetic energy is energy associated with a state of motion of an object. State means the condition of an object. For an object of mass m, and whose speed v is well below the speed of light, we define the kinetic energy k equal half mv squared. This energy is proportional to v squared, so it can never be negative, always positive. Kinetic energy can never be negative. The metric system unit of kinetic energy is Newton meter, a joule. 1 Newton meter, 1 joule equals 1 kilogram meter square over second square. Another unit of energy when dealing with atoms or with subatomic particles is electrovolt. We denote EV. 1 electrovolt equal to 1.60 times 10 to the minus 19 joule. This is a very small unit, so we often use the kilo EV or mega EV. Sample. In 1896, in Fargo, Texas, William Crush of the Katy Railway parked 2 locomotives at opposite end of 6.0 kilometers long track. Fire them up, tie them throttles open, and then allow them to crash head-on at full speed in front of 30,000 spectators. Hundreds of people were hurt by flying debris. Several were killed. Why? As energy. Assuming each locomotive's weight 1.2 times 10 to the 6 Newton, and its acceleration along the track was a constant 0.26 meter per second per second. What was the total kinetic energy of the 2 locomotives just before the collision? Now, the kinetic energy is the sum of these 2 motor locomotives, so equal to mv squared. We found a v because this is a constant acceleration motion. We use this formula, v squared equal to v0 squared plus 2as, where this is what we want to find. v0 squared 0, starting from at rest. A is 0.26, and x minus x is its distance travel, is half the track long. 6.4 times 10 to the 3 over 2. That is 3.2 times 10 to the 6. So we calculate, you get the V. So once you V, we need M. M is equal to W over G. So we know its weight, we know G, so we get M. We put this number inside. We get the number. It's very huge. 2.010 to the 8th joule. How big it is? It is equivalent to 100 pound TNT. You know TNT is an explosive material. Work and the kinetic energy. Work, the energy of an object changes if an exchange of energy occurs between the object and its environment. Such a transfer can occur due to a force or due to an exchange of heat. We discussed the exchange of heat in other chapter. Here, we discussed the transfer of energy via force, a process known as doing work. Work W is the energy transferred to or from an object by means of a force acting on the object. Energy transfer to the object is positive work, and energy transfer from the object is negative work. Work then is transfer energy. Doing work is the act of transferring the energy. Work has the same unit as energy and is a scalar quantity. The term transfer can be misleading. It does not mean that anything material flows into or out of the object. Work and kinetic energy. Let's now relate the work done on an object by a force and the corresponding change in the kinetic energy of the object. If the force changes the speed of the object, it also changes the kinetic energy of the object. Work done by a single constant force. Single force, constant force. We look at the situation. A bit is moving along x-axis with displacement d. Under force, this force is single, constant. Constant means during the motion, its direction and its magnitude does not change. Phi is the angle between F and X. This must be a constant acceleration. So we have this formula v squared equals v0 squared plus 2ad, where a is acceleration along x direction. We multiply 1.5 on both sides. We have this new look at it. And here we see half and 2 cancel out. max, which is the fx. This is the component of forces on x-axis. We rewrite this equation as k final equal to k initial equal to f to d. Half mv squared is the kinetic energy at the final stage. Half mv squared is initial kinetic energy, and this is the work done by the force. If the kinetic energy is the only types of energy of the object being changed by the force, then the change delta K in kinetic energy is equal to the work done by the force. Delta K, K final minus K initial equal to W. Or K final is equal to K initial plus work done by the force W. Work-Kinetic energy theorem. Half mv final square minus half mv initial square equals F dot D, the work done by the force. This is the dot product by two vectors. So by definition, it is equal to F D cosine phi, where phi is the angle between these two vectors. So we rewrite it with the df cosine phi. This is the component of f along the displacement of d. To calculate the work done on an object by the force during a displacement, we use only the force component along the object's displacement, f cosine phi. The force component perpendicular to the displacement does zero work. Work done by a constant force can be rewritten as this: F equals F dot D. The dot product equal to Fd and the cosine phi, where phi is the angle between the directions of the displacement d and the force F. W equal F dot D equals Ft cosine phi. If F is in the same direction as D, so phi is smaller than 90 degrees, cosine phi is positive. It's positive work. If F is opposite the direction of D, they are opposite direction. The phi is between 90 degrees to 180, is a negative number, so the work done is negative. A force does positive work when it has a vector component in the same direction as the displacement, and it does negative work when it has a vector component in the opposite direction. It does zero work when it has no such vector component. In other words, phi is 90 degrees. Net work done by several forces. When two or more forces act on an object, the net work done on the object is the sum of the works done by the individual forces. For example, we have many forces. The net force sigma I, Fi, is equal to F1 plus F2 plus F3, and so on. The work done by these forces is equal to net force dot D. We put this sigma Fi in, we get F1 dot D plus F2 dot D plus F3 dot D, and so on. And F1 dot D is the work done by F1. F2 dot D is the work done by F2, and so on. Work-kinetic energy theorem. Delta K equals K final minus K initial equals work done by the force. Rewrite it: half mv final square minus half mv initial square equals sigma Fi dot D. If the object's energy other than kinetic energy is being changed by the force, then above equation do not apply. A kinetic frictional force, for example, can change both the kinetic energy and the thermal energy of an object. In that case, they do not apply. Thermal energy is associated with the random motions of atoms and molecules within an object. Sample. Figure A shows two industrial spies sliding an initial stationary 205 kilogram floor safe, a displacement d of 8.50, straight toward their truck. The push F1 of spy 001 is 12.0 Newton, direct at an angle 30 degrees downward from the horizontal. The pull F2 of spy 002 is 10.0 Newton, direct at 40 degrees above the horizontal. The magnitudes and the directions of these forces do not change as the safe moves, and the floor and safe makes frictionless contact. A. What is the net work done on the safe by forces F1 and F2 during the displacement D? We look at free body diagram of the safe. Forces acting on it. Normal force from the floor, gravitational from the earth. Push F1 from the spine 001 and pull F2 from spine 002. The result, it moves along the direction with displacement D. The work done, let's look at F1. F1 is F1 dot D equals F1D cosine phi 1. Here phi 1 is the angle 30 degrees. They are positive. This is F2, W2. W2 is F2 cosine phi 2 is the component of F2 along the displacements. Okay, so this is what? The net work done on the safe 4K, you put together. We take three significant figures as given. So it's 153 joule. Question 2. B. During the displacement, what is the work WG done on the safe by the gravitational force FG? And what is the work Wn done on the safe by the normal force N from the floor? By definition, the direction between the gravitational force downward and the displacement horizontal is 90 degrees. So this work done is 0. Also true for the normal force, because the angle between the normal force upward and the horizontal is 90 degrees. So this is 0. Question C. The safe is initially stationary. What is its speed, V final, at the end of the 8.50 meter displacement? So we have the work then is equal to the kinetic energy change. We put this number in, we get a sum. Vi is 0 initially, so we get this number easily. Okay, W2 over m square rho. Sample. During a storm, a crate of cream is sliding across a slick, oily parking lot through a displacement D equals minus 3.0 I. While a standing wind pushed against the crate with force F equals 2.0 I minus 6.0 J. The situation and the coordinates exist are shown in the figure. These coordinates. Question A. How much work does this force from the wind do on the crate during the displacement? By definition, W equals F dot D. F is 2.0 I minus 6.0 J. D is minus 3.0 I. So Ij is a constant. So we do this one, rewrite this one. 2.0 minus 3.0 dot I dot I. Minus 6.0 minus 3.0 J dot I. We know I dot I is 1.1 cosine 0 is 1. J dot I, they perpendicular, equal to 1.1 cosine 90 degree is 0. So this term is 0 because J dot I is 0. So we get this I dot I equal 1. We get minus 60. Question B. If the crate has a kinetic energy of 10 joule at the beginning of displacement D, what is its kinetic energy at the end of D? It's very simple. K final equal to Ki plus W. That equals 4.0 joule. In this case, because kinetic energy is the only change of energy, so we can use this theorem. Work done by gravitational force. Look at this picture. This is a tomato was thrown up at initial speed v0. We look at this because the work done by the gravitational force equals mg dot d. The displacement d is upward, the gravitational force acceleration is downward. So the angle between them is 180 degrees. So this is a -1. So in this case, the work done by the gravitational force is negative number. So we get the final kinetic energy equal to initial kinetic energy plus some minus number. It is smaller than the initial kinetic energy. So that's why it slows down. We look at the kinetic energy change. It is kF minus ki, and it is half mv squared minus half mv0 squared. And on the right side, the work done by the gravitational force is equal to mg dot d. G is always downward toward the center of Earth. If the displacement d up, then the angle between them is 180. So cosine 180 is -1. So in this case, GW is smaller than 1. KF is smaller than K initial. On the other side, G is always down if the displacement is downward. And they are in the same direction. The angle between them is 0. Cosine 0 is 1. So in this case, the work done by the gravitational force is a positive number. And the final kinetic energy is larger than the initial kinetic energy. Work done in lifting and lowering an object. Now, we hold an object, move it up or move it down. What happened? We see the kinetic energy K final minus K final equal to sigma W, the work done on it. In the case, we have two forces. One is applied forces, W applied. One is gravitational force, G. Applied force have done work F dot D, and gravitational force to the one mg dot d. In case if the object is stationary before and after the lift, then we see K final equal to K initial equal to 0. And put this inside, we find the work done by the applied force equals minus the work done by the gravitational force. Sample. An initially stationary 15.0 kilogram crate is pulled by a cable at distance d 5.70 meter up a frictionless ramp to a height h 2.50 meter, where it stops. Question A. How much work WG is done on the crate by the gravitational force Fg during the lift? We write down the free body diagram. Three forces acting on this crate: pulling force T, normal force N, and gravitational force F. What the work done by WG? By definition, it is gravitational force mg dot displacement d. In this case, d is up, great force up. So the angle between them is phi is 90 degrees plus theta. So this mgd cosine theta plus 90. This is equal to minus sine. And we see d sine theta. This is theta. This is d. D sine theta equal to h. So this is equal to minus mg h. We put them inside. We get a number. Minus 368 joule. Question B. What is the work WT done on the crate by the tension T of the rope during the lift. That's the definition. The definition. Delta K equals sigma F W. W in this case including 3. 1, 2, 3. 1 by the pulling force, 1 by the normal force, 1 by the gravitational force. So this one, because initial state and the final state all are stationary, so this is equal to 0. And then that means the sum of these 3 works put together is 0. And we know the normal force dot D is equal to 0 because the angle between the normal force and the displacement is 90 degrees. Cosine 90 degrees equals 0. And we just now find the WG. So we put this equation, we find Wn. The work done by the pulling force T is minus this one, is positive 368 joule. Sample. An elevator cap of mass m 500 kilogram, descending with speed v0 4.0 meter per second. When its supporting cable begins to slip, allow it to fall with a constant acceleration a equals g over 5. Question A. During the falling, throw a distance d 12 meter. What is the work done by the gravitational force on the cap? We look at free body diagram. This is the cap, the force pulling force T, gravitational F, and it's falling down. I want to find the work done. Very simple. It's gravitational force dot D. They are in the same direction. So that means mgd cosine 0 mgd. We put a number inside, we get a number. Question B. During the D12 meter fall, what is the work WT on the cap by the upward pull T on the elevator cable? By definition, WT equal to T dot D. Because the T and D are in opposite direction. So there's a TD cosine 180. This is minus 1 equal to TD. At the same time, we know that T minus mg equal to m8. We know A. The A is g over 5. So T equal to ma plus mg equal to minus g over 5. This is going up, plus mg, we get equal to 4mg over 5. We put the number inside, we get the answer. This is a minus number. Question C. What is the net work W done on the cap during the fall? We see that only 2 forces. So we put them together. One is 5.88 times 10 to the 4. One is minus 4.70 times 10 to the 4. So we get 12 kilojoule. Question D. What is the cap's kinetic energy at the end of the 12 meter fall? In this case, kinetic energy is the only energy changes. So we can use the work-kinetic energy theorem. W, work done, equal to K final minus K initial. So the final kinetic energy, Kf equal to W plus K initial. The work done is 12 kJ. The Ki is half mvi squared. We put the number inside, we get the answer at 1.56 times 10 to the 4th. Take 2 significant figures, we get it. Round up, 16 kilojoule. Work done by a general variable force. one-dimensional analysis. We have a force, F, which is a not constant, is a variable force. F changes with X. What the work done by this variable force? Let's do the approximation. We divided the area by many strips, and each strip is with delta X, and the height is the average F in this area. So this strip area delta Wj equal to Fj average times delta X. And we put all these strips together. That approximately equal this area. When the delta X approaches 0, very narrow, so this average exactly is equal to Fx. This average is approximately Fx. And we let delta X approach 0. So we have so many strips put together. And this area is almost equal to the real one. When X should approach 0, the F average is equivalent to Fx. So we change it to Fx. And we look at this one, sigma limit epsilon. This is the definition of integration by Newton. So the work done by a variable force in one-dimensional is F dx integration. From where to where? From x equal to xi to x equal to x final. That's the conclusion. We're doing this one, this area, delta x plus 0, like this one. Exactly the one we want. So we get the answer. The work done by a variable force is equal to integration. Three-dimensional analysis. Three-dimensional, the delta W equal to F dot dr. Because it's changing all the time, we take the very small dr. F, we know that equal to fxi plus fyj plus fck. Dr equal to dxi dy dk plus dzk. By definition, the dot product by two vectors equal to fx dx plus fy dy plus fz dz. Then we put them together, integration. The total W is equal. Integration is sigma integration. From where to where, we know at the beginning its position is Ri equal to xii plus yij plus zik. So we started from Ri. And this one is xi, this is yi, this is zi. And when it ended as this one, it's called the R final equal to x final I plus y final j plus z final j. So we put them down. This is R final, this is x final, y final, z final. That's it. That's it. Okay. It's extension from the one-dimensional world. Work-kinetic energy theorem with a variable force. With small, still from very small dw started. And we see Fx equal to ma. What is A? A is dv dt. And we know this differentiation, we can separate the denominator and the numerator. So we change dv with dx. We get a dv out, dx in. And what is this? dx dt is v. So it becomes v dt. And we put them inside, you get this half mv squared. You do the derivative half mv squared relative to the v, we get this one. Okay? So dw equal to d half mv squared. We rewrite this dw equal fx dx equal d half mv squared. And the total energy is the integration. So we do the integration, we get a total work. And let's see, when V equal to VI, X equal to XI. When V equal to VF final, X equal to F final. So this is the work done. This is a kinetic energy change. We do this one, okay? We do this one. So this one equal to half mv final squared minus half mv I squared. This is the final kinetic energy. This is the initial kinetic energy. So that is delta K. We prove works kinetic energy theory with a variable force. Sample. Force F 3x squared I 4j with x in meters. X on the particle, changing only the kinetic energy of the particle. How much work is done on the particle as it moves from coordinates 2, 3 to 3, 0? Does the speed of the particle increase, decrease, or remain the same? As the formula, dW equals F dot dr. In this case, F is two-dimensional vector. So this two-dimensional, we write this one. This equal to fx dx integration plus fy dy integration. If it is three-dimensional, we have extra mode, extra term, integration fc dz. Now, we put the number inside. First, fx equal to 3x squared, 3x squared. And the limit is 2 to 3. So it's 2 to 3. And for the second term, fy equal to constant 4. And the limit is from 3 to 0. 3 to 0. Finally, we get 7.0. Work done by a spring force. The spring force. We see a spring stuck attached a block attachment. This shows a spring in its relaxed state. That is, neither compressed nor extended. It's natural length. An axis has been placed parallel to the length of the spring with the orange x 0 at the position of the free end when the spring is in relaxed state. What is relaxed state? Neither compressed nor extended. Remember, x0 is at the relaxed state. It's not the length of the spring, okay?
Energy can be stored in many ways. Compressing a spring, for example. We'll use this glider floating on an air cushion to show just how much energy is stored in a spring for a given amount of compression. This arm attached to the glider will compress the spring contained inside this glass tube. To determine how the energy stored in the spring varies with different compressions, we will compress the spring by 3 different distances and then use the energy stored in the spring to launch the glider up a tilted track. The spring energy will be converted into kinetic energy, then into gravitational potential energy, which is directly proportional to the height of rise of the glider. We launch the glider with the spring compressed 1 unit, and it rises up the track 1 unit as measured on the bottom scale. If the spring is compressed 2 units, how high will the glider rise? If the compression is increased 3 units, how high will the glider rise? The energy stored in a compressed spring is proportional to the square of the compression distance.
When a ball bounces after being dropped, it will not normally bounce higher than its original height. When we drop this object, it bounces higher than its original height. How can we explain this behavior? The object is a handball cut in half. Before it was dropped, it was flipped inside out, storing energy in the elastic material. When the half ball hops back to its normal shape, it has enough energy to go higher than the original height.
Many forces in nature have the same mathematical form as the spring force. That's so crucial. To a good approximation, for many springs, the force F extended by the spring is proportional to the displacement d of the free end from its position when the spring is in relaxed state. F equals minus kd. K is larger than 0. This is a Hooke's law. We look at this one. This is a natural relaxed state. We pull it, it has force this one. We push it, it had a force this one. K is the O's negative direction of displacement. F equals minus kx, Hooke's law. The minus sign of the Hooke's law indicates that the spring force is always opposite in direction from the displacement of its free end. You put it x, displacement is d to the right, and the force is to the left. If we push the spring, the displacement is into the left, and the force against you is to the right. It's always opposite in direction. The constant K is called the spring constant and is a measure of the stiffness of the spring. Note that a spring force is a variable force because it depends on the position of the free end. F can be simplified as Fx as a function of x. Work done by a spring force F equals minus kx. This is work done by the spring. Since it changes, so we can divide it into many small sections. Each section is the work dwi, and then we put them together. Okay, and this fx is minus kx. So we put minus kx inside and change this to integration. This becomes integration fx dx from xi to x final. From initial position to the final position. Fx equal to minus kx. We put this one inside, and this is a very simple integration. We get this is half kx final minus half kxi. So this is positive, this is negative. Look at this one. It's all square. If the x final equal to xi, for example, you push this xi, you put it up, x final. Even the length of the spring is different, but this is equal, so the work done by the spring is 0. If the final length from the free end is smaller than initial length, the work done is by the spring is positive. Vice versa. X final larger than x initial, the work done by the spring is more than 0. Work Ws is positive if the block ends up closer to the relaxed position than it was initially. It is negative if the block ends up farther away from x0. It is 0 if the block ends up at the same distance from x to 0. When they equal, it might not equal. One is positive, one is negative. Okay, they might not be the same. So usually when xi is 0, starting from the relaxed state, this is 0. So we get the work done by the spring is minus half kf final squared. The work done by an applied force in the spring case We know delta K equal to K final minus K in equal to two forces. Applied forces, spring force. So do work 2. If the kinetic energy change is the only change of the energy. If V final equal to Vi equal to 0, all stationary at T equal to 0 and T equal to T final, then we find this is 0. And we find the work done by an applied force equal to minus work done by the spring force. If a block that is attached to a spring is stationary before and after the displacement, then the work done on it by the applied force displacing it is the negative of the work done on it by the spring force. Sample. In the figure, a chromium canister of mass m 0.40 kilogram slides across a horizontal frictionless counter with speed v equals 0.50 meter per second. It then runs into and compressed a spring constant K 750 Newton per meter. When the canister is momentarily stopped by the spring, somewhere here, by what distance d is the spring compressed? We'll find the compressed distance. It's very easy work. We see that the work done by the spring is minus half kx squared. We put it to the top. This is the distance d equal to half kd squared minus. And this one should equal to the kinetic energy change. The finally is stopped here. Initially it has v squared. So we put this one inside, we say these are the same thing. We equal these two, we find v d squared equal to m over kv squared. So d, you put a number inside, you get a number. It's about 1.2 centimeter. Power. The time rate at which work is done by a force is said to be the power due to the force. If an amount of work W is done in an amount of time delta T by a force, the average power due to the force during that time interval is P average equal to W over delta T. The instantaneous power P is the instantaneous time rate of doing work. P equal to dW dt. Since W equal to F dot R, if the force is a constant, then F can take it out. We get F dr dt. And dr dt is velocity. So the instantaneous power P is equal to F dot V. This is under condition constant force. Unit of power. The symmetric system, watts equal to joule per second, the word per second, joule per second. Another unit is called horsepower, equal to 746 watt. Another unit of power we call kilowatt hour. This is a 1 degree electricity. 1 kilowatt hour, which equal to 3.60 times 10 to the 6 joule, 3.60 millijoule. Sample. Figure shows constant force F1 and F2 acting on the box as the box slides rightwards across a frictionless floor. F1 is horizontal with magnitude 2.0 Newton. F2 is angle upward 60 degrees to the floor and has magnitude 4.0 Newton. The speed v of the box at a certain instant is 3.0 meter per second. Question A. What is the power due to each force acting on the box at that instant? And what is the net power? Is the net power changing at that instant? Okay, we see, study from the definition. Power 1 if F1 dot V. If F1 cosine phi 1. This is 180 degrees minus 1. So we get minus 6.0. This one, F2, P2 equals F2 dot F equal to F2V cosine 60. This is a, you get positive 6.01. So put them together, instant power is 0. Next lecture, Chapter 7, Potential Energy and Conservation of Energy. Welcome you make a comment and give suggestions so that this program can be more helpful. Acknowledgement. This video clip is a part of my lectures on college physics during 1990 to 2021, based on the adapted textbook Principles of Physics by Holliday, Resnick, and Walker, published by Wiley. The demo videos were bought from a company in USA by my university for teaching. They helped a lot. I'm sorry for not remembering its name to show my appreciation. It seems that they came from the University of California, Santa Barbara, where I got my PhD in physics. Thanks God.